Hello everyone, and welcome to episode 6 of the CS Education Zoo. I'm your host, Steve Wolfman, and my regular co-host, Will Bird, was unavailable today, unfortunately, but we have our special guest co-host, Dutch Meyer, with us. Dutch, you want to give everybody a wave? All right, awesome. Today we have a fabulous guest. We've got Mark Guzdial with us. I'm gonna look over here now and read my bio. So everybody, when I look off to the side of the screen, it's because I'm looking at my other screen with my notes and my questions, that sort of thing. So Mark is a professor in the School of Interactive Computing at Georgia Tech in the College of Computing, and he studies how people understand computing and how to make that more effective. He's a PI on the CS Learning for You effort to create ebooks to help high school teachers learn CS. And he was a PI on the NSF-funded Georgia Computes Alliance for broadening participation in computing, which was also very involved in high schools. And is a PI on the new NSF Alliance expanding computing education pathways. He invented media computation, and he's published several books on the use of media as a context for learning computing. He's on the editorial boards of the Journal of the Learning Sciences, ACM Transactions on Computing Education, and Communications, the ACM. And with his wife and colleague Barbara Erickson, he received the 2010 ACM Carl V. Karlstrom Outstanding Educator Award. He was also a recipient of the 2012 IEEE Computer Society Undergraduate Teaching Award, and he is a personal computing education hero and mentor of mine who's helped me out a lot in the past. So without further ado, let me put Mark on. Do you want to just say a few words of hello, Mark?
Hello, everybody. Glad to be here. I've watched the previous episodes, and I'm looking forward to this. This should be fun.
Awesome. So I'll just start out with a question I've been wanting to ask you for a while, and I guess everybody gets to ask you this by reading your blog, but I thought I'd ask in person, and that's, what are some of the promising directions you see the practice of CS education going in the coming years?
Promising in the sense of this is something that everybody ought to do, or promising in that I'd like to see it happen one day?
Ooh, good question. Let's start with you'd like to see it happen one day.
I'd love to see more live coding in classes. I'd love to see more coding for other kinds of purposes and coding integrated into other classes. Live coding. So I got invited to a Dagstuhl seminar last year, 2 years ago. It was so Dagstuhl is this really interesting place in Germany, Schloss Dagstuhl, where they invite CS people to talk about some seminar topic, and you stay there for several days, and there's nothing around it, so everybody stays there and talks about it. And I got invited to one about live coding. From the computer science education perspective, when we think live coding, we think about somebody programming in the front of the classroom, which is a really good practice. Lisa Barker and Eric Roberts have called it a best practice for teaching computing. For lots of reasons, people get to see students get to see your process. The students get to see you make mistakes, and then get to see you recover from them, and they come to the realization, oh, even the teacher makes mistakes. Everybody gets mistakes. It's okay to get mistakes in computer science. So I got invited because I've talked about live coding as being a really useful thing. But it turns out that's not what they think about it. I got invited to a group of musicians. There are these musicians who will program live in front of an audience, and they write programs that generate music, and they do this collaboratively. So one person starts writing code that makes music, and then the other one joins in, and they're riffing off of one another, and they build their own programming environments. They build their own programming systems. It's beautiful. It's really interesting, and it really changes your notion about what programming is about. Right? Here, it's not about developing a piece of software that's going to be canned for thousands of people to use. It's about building something now, in the moment, responding to things around me for the enjoyment of the people in the audience. What a dramatically interesting way of using coding. And things like that, I think, coding to me is a literacy. Programming is a literacy. And you use it to express yourself and to communicate with other human beings. And I don't think we do enough of that. Live coding is totally that. It's about writing code in order to generate music for the people around you, and they're seeing your code. I'm really interested as a CS Ed researcher to try to do some studies of the people in the audience. You figure that most people in their everyday lives never see a programmer, never see programming, don't know what code looks like. What do people who go to these live coding concerts, or even dance halls? There's amazing videos at toplap.org where you can see live coders in front of a dance hall coding and people dancing to the music that's coming out of their programs live. What do the people in the audience think about coding after seeing that? They see the code, they dance to the music. How does their perception of what is computing change? That's a direction I'd love to see computing education go more in. Things like what Uri Walensky and Irene Lee are doing with taking computing and embedding it in science classes, embedding it in math classes, the Bootstrap project, using computing as a way of coming to understand Algebra 1. I love those ways of thinking about coding beyond just to hack software. It's about expression. It's about understanding things in new ways. So to me, that's a really exciting direction for computing education in the future.
That is totally fascinating. Can you? So you mentioned toplap.org. Is that where we should go to see this group? Okay.
Yeah,
Awesome.
that's the main place where the live coders meet. There's actually a live coding conference going on in Brighton, England, this very weekend, including a doctoral consortium. There are people who are working on their doctorates about live coding. The live coders they build these incredible systems. One guy built his all the way down, Andrew Sorensen, down to LLVM. He actually spits out machine code, all in terms of his system. Alex McLean built his system on top of Haskell. They use these really innovative programming tools like temporal recursion. It's a whole new way of thinking about coding. It's very powerful and really interesting.
Are they building things besides music?
Yes, in fact. So they're at the Dogstool. There were a few oddballs like me doing education stuff, but there were also folks exploring things like weaving, writing code to generate weaves. And I'm going to blank on the scholar's name who came to the seminar, but she studies how weaves have been done in the past and tried to figure out how to generate them. And there are weaves for which you can generate an algorithm, but current looms, current weaving machines can't actually generate those weaves. And so it's this really interesting way of thinking about algorithms in ways that we don't yet know how to make a machine to implement that algorithm.
I probably exposed my own bias by saying my first thought goes to fighting robots.
Yes, I would say that exposes your bias. Absolutely, yes.
So let me ask you a follow-on question to that. That's so fascinating. I live code in one of my classes right now. It's a programming languages class, develop interpreters to show people what's under the hood of the semantics of programming languages. Is there anything I should be thinking about as I do that, or is it enough for me to just get up there and do my thing?
Yeah, I think the important thing to do when you get a bug is to slow down and explain what you're thinking about, doing thinking aloud. Folks, there's this paper called Cognitive Apprenticeship by, let's see, it's Alan Collins and John Seeley Brown and Paul DeGewitt. And Cognitive Apprenticeship really influenced me when I was doing my dissertation. The idea is that a cognitive apprenticeship is challenging. The traditional apprenticeship has a lot of pieces to it. The master is going to model a particular activity. The apprentice watches what happens and then replicates it with the apprentice coaching. But when you're talking about cognitive activities like mathematics or reading or computer science, you can't see the cognition going on. And so it's really important for the teacher to make obvious, to make explicit what their thinking processes are so that the student can follow along and learn from it. And it's really hard to do because I know for myself, you get a bug in class. I mean, you know, you probably get this too on your teaching evaluations. It was so nice of Professor Guzdial to make those mistakes in order to demonstrate to us how to correct them. No, I just make mistakes, right? There's nobody in the world who can hack in front of 100 people and not make mistakes. And my first inclination is, oh, crud, what did I do here? How do I fix this? But I got to realize that it's a teachable moment. Exactly. I don't want to hide, right? I want to say, oh, okay, wait a minute. This is what I thought was happening, or this is the typo that I made. This is what's really happening. Here's how I'm going to fix it. And you've got to say it in terms that your audience, your students, are going to understand. because it's really easy for you to simply jump to a conclusion, oh, oh, I know what it is, fix, right? When that's not going to help the students very much. It's really hard for experts to make explicit the knowledge which is innate, which they've done so often, you know, poof, you immediately see where the semicolon is missing, or poof, you immediately see where you have the type mismatch. But for the students, that's the opportunity to slow down and say, oh, okay, it could be this, it could be this, here's the evidence that it's actually this, what's my fix, I could try this, I'll actually try that. Making that explicit is really important for the students when you're doing live coding.
Are there ways to, so my programming is built from hundreds of habits that I've built over decades of programming. Are there ways to get across those habits, which ones you've chosen and why, without overwhelming the students with too much information?
Can you give me an example? What kind of habit?
So for example, when I do an opening parenthesis, I close it immediately. And then I back up to make sure that I don't miss the closing parenthesis.
Yeah. So I think that's a great practice. I think that doing it, telling students why you're doing it, and then making sure that you're consistent in doing that thereafter will encourage the students to try to adopt your practice. I mean, one of the challenges of that one, in particular, I think that is really interesting, is that you do that because you have a certain humility about your coding, right? You recognize, I make mistakes like this. I make mistakes like this all the time. I am going to adopt this particular practice to try to keep myself from making mistakes.
Absolutely.
That's really hard for students to get. It's really hard for students to get that, that you have to expect errors. I'm teaching a senior design right now, and you know, they get it innately now. Yes, my code probably has some bugs in it, but they don't want to admit that they have bugs. They don't want to think about it as having bugs. They don't think about that process of, you must assume there's this number of bugs. Do enough testing so that you know that you've caught this number, because that number will still be less than the number that are actually there, but you'll get a good bit of them. And this is something that Ifat Kalikant wrote about in ICER 2005, that students' notion of being right is way different than ours is. She had this wonderful example of where the students were supposed to do some calculation and come up with some number. And the students struggled with this and had all kinds of print statements and printed out all kinds of stuff. And then what actually displayed, yes, the right number was in there. Well, it was, you know, in the middle of 75 lines. And the teacher said, you know, this isn't right. The student says, it is too. The answer's right there, see? And you have to explain, no, that's not right. What right is that you do exactly what I asked you to do. You have to meet the requirements. And so what students seeing as being right, what students think as being debugged, is a very different sense than ours. And I think that it is a kind of practice of mind that is useful to teach students to have that humility, to expect that your code is wrong and that you're going to have to fix it somehow. Or do things to avoid the errors as you're describing.
I'm write that down right now because I really want to record that. So if you can riff for another minute, that would be great.
All right, so I'll riff on the other version of the way of interpreting your question. You asked about the future of CS education, and I told you about what I'd like to see happening. Another thing that I could see happening, that I'd love to see happening, is to take some of the things which we have pretty darn good support for from research and actually see them more in practice. So, for example, things like pair programming, things like peer instruction, media computation if you're having a problem with retention. I think that our evidence that media computation improves retention is pretty strong. The evidence for pair programming and peer instruction is really strong. There's also a bunch of practices that I would love to be banned for all time from CS education classes that we now know is a bad thing to do that still happens pretty regularly. I just talked to a student who's telling me about her Java class, where the Java class in this sequence is the second part of the second course in the sequence. The first course is Python, and he asked for a show of hands. How many people in the class have had Python before? Some people, of course, raised their hand, most of them actually. And he says, Python is a terrible language. You must now forget everything you had to know about Python in order to be able to learn Java well. And we know that that is an absolutely horrible thing to say to students, even if you really believe it, and even if you're just doing it to joke around banter. We have evidence from Margolis and Fisher's work and Unlocking the Clubhouse and lots of other work since then that that's the sort of thing you say if you want to make all of the women and underrepresented minorities in the class say, oh, really? I really don't know what's going on. I learned this language, Python, and that's a bad language. The teacher just told it to me. I'm even more of an imposter than I thought I was. So I'd love for us to never again say things like, oh, if you're using a Mac, you're not using a real computer, or Windows, depending on what your religion is, that Python is a terrible language, that your experiences that you've had in the past have ruined you for all time. I'd like all of that to go away. Was that a minute?
That was what I needed. That's good. Okay, so I'm gonna pivot now and move over to your work on high school CS education, and I wanted to just start by asking how we should be preparing CS teachers in high school.
Okay, so the first lesson is that we shouldn't be preparing them the way that we prepare CS undergraduates. The job of being a computer science teacher is a different job than being a software developer. I've been thinking about this lately in terms of the HCI first dictum. I'm sure that both of you are well aware that the very first thing you learn in HCI class is know thy users, for they are not you. You cannot use yourself as a model for what the users are expecting or what the users want. You can't use your education as a CS professional or a CS professor or as a CS expert in any way to use as a model for what it is that a high school teacher needs to know. Some of what we've learned is that our very best high school teachers, the ones who recruit hundreds of students and successfully move them on to advanced placement computer science, the very best ones of those write almost no code ever. Instead, they read lots of code. They comment on lots of code. That's a very different set of skills than what we expect a software engineer to have. We also expect a high school computer science teacher to know a lot about what's called pedagogical content knowledge. Content knowledge is obviously about computer science. Pedagogical knowledge is things like how do you run a class and how do you write a syllabus and using things like peer instruction. Pedagogical content knowledge is the knowledge about how to teach that. And there was recently a really cool research project out of Harvard by Phil Sandler where he came up with a measure for pedagogical content knowledge. He took a bunch of science teachers, and he has a test for the science knowledge that they're going to be teaching, and gives it to the class at the beginning and end of the class, and he gives it to the teachers twice at the beginning of the class. The first time, please answer the questions as correctly as you possibly can. Second time, please answer the questions in the way that you think your students will get it wrong most often. What is the most common distractor in each of these multiple choice questions? The teachers whose students made the biggest gains pre-test to post-test were the ones who got it right in both cases. They knew the content and they knew what the students would get wrong. There's a bunch of things that we now know about how students will get wrong. My daughter is in AP Computer Science right now, and so she had a test 2 days ago, and so I had her and her friend over on Sunday and tutored them in Java. Brought up Dr. Java and Barbara's Turtles and Worlds, and we played with Java. And I saw them making all of the classic misconceptions that we know about the intro Java level, right? So I say, okay, A equals B. What does that tell me what's in A? Well, what's in B? Nothing, because I moved it into A. No, actually B still has its value, but that's a really common misconception. Knowing about things like that, if a teacher doesn't know about those sorts of misconceptions, they're sort of going to fall off the cliff because they don't know what sort of problems their students are going to have. So you want teachers to know pedagogical content knowledge. That's not just about how an assignment works. That's not just about how to teach your classroom. It's about what the students will get wrong, how to identify it, and how to fix it. So my first, biggest, most important lesson that I've learned about teaching high school teachers is you can't teach them the way you teach CS undergraduates or the way you teach CS professionals. They're trying to learn different skills. They need additional content that we're not teaching in our normal computer science classes.
So I'm guessing Most of what you said there would also be true of those of us teaching university level computing courses.
Well, in terms of things that you need to know, sure, pedagogical content knowledge would be super useful for people who teach computer science at the undergraduate level too. Um, I don't have much hope that I can convince all undergraduate computer science teachers in the world to go get that kind of knowledge. I mean, the best of them do. I'm going to bet, Steve, that you know gobs of those sorts of things that people get wrong regularly in your classes. I mean, I know I get to the point in media computation where students will tell me there's a bug in their code, and they'll show me the output, and I can tell them where the error is without seeing the code. Because I've seen gobs and gobs and gobs of these over the last 10 years. So, you know, when I see one line of pixels and that's it, I know that you got you're moving only the Y loop or the X loop, not both. And so you're just mapping all the pixels to one line or something. You just know, you get to know those sorts of things. And good teachers keep aware of those things. They reflect on them. They think about how they can diagnose them and how they can correct them. But as you are probably pretty familiar, that's not a requirement to being a computer science teacher in undergraduate anywhere.
Yeah, definitely. Let me ask one more little follow-up on that. I noticed when you were sort of having the imaginary conversation with your daughter and her friend or friends, when they had that misconception, the first thing you said was, yeah, that's a really common misconception, as opposed to just going in and addressing it. Is that something that's important?
That's really interesting. Yeah, I do that, and I'm not even aware that I'm doing it, but you're probably right. I mean, I did say that to her at the time. No, that's not quite right, but don't worry about it. A lot of people think about it that way. So I was explicitly trying to soften the blow of getting it wrong. I was explicitly trying to say, oh, I get that. That's
Uh-oh, it looks like we may have lost Mark. Dutch, are you hearing Mark?
I'm not. He has stopped.
Okay, so for everyone in the audience, this is our commercial break. Mark mentioned to us that he is great wireless in his building, but he's the one who's furthest from the hub. So maybe we can just take a moment.
Yeah, this is a great time to remind everyone that the CS Education podcast is brought to you by the programming language C, which combines the power of assembly language with the readability of assembly language.
Now hold on. We're not saying anything bad about particular.
Nothing, not against it. No.
Yeah, those are actually kind of cool features of C if that's what you're looking for. Yeah. Okay, well, we usually take a moment towards the end to mention what might be coming up in the zoo. So I did want to mention really briefly that Will is working on maybe getting us several of the people from Hacker School to come and talk to us about what they do. That'll be our first CS Education Zoo where we've got multiple guests. So hopefully that will go great. And that's what I've got. I'm just going to give Mark a quick message and let him know we're hoping he'll rejoin.
Yeah, and we've got a paparazzi picture of him up on the screen here. Yeah, I'm curious to ask Mark more about media computation, because I started programming in HyperCard, as many of my contemporaries did. Which I think, I don't know much about media computation, but I think he probably would call that an example. Here we go.
Welcome back.
I don't even know when it gave up. I mean, I was talking and suddenly noticed, wait a minute, neither of you are moving. What happened? I'm so sorry.
I forget the exact sentence, but your pose was something like this.
Let's see, you would ask me if I normally say to my daughter things, or in general when I'm doing this sort of thing, if I'm saying, yes, that's a common misconception. And I was saying, I'd never even been aware of that, but yes, I think that is a positive thing to do, and I do notice that I do it. I'd started to tell the story. I taught a class last spring, and it was a freshman level class, and I have a daughter who's a sophomore here at Georgia Tech, and so she knew people who were in my class. And she told me, oh, the students are saying it's going really well, They said they like how you compliment them on their questions. And she said, oh, that's just what Dad does. He does that all the time. And I wasn't aware of it, but it is the case. I often say, oh, that is such a good question. There's a lot of cool things that we can talk about in response to that. So, yeah, there's some things that you just do as a teacher and figure them out later.
Now, sometimes you need to be reminded, though, so thank you for that.
Yeah.
Now I'm going to spill a little bit about how the sausage gets made here at the CS Education Zoo, and one of the things we do is we ask our guests if there are any questions they want us to ask them, and you gave us a really beautifully juicy one, so that's up next.
All right.
Following up on high school teachers, which is more important, to have CS education in high schools or to have high quality CS education in high schools?
So, in part, it depends on what your goal is. If you want students to come into undergraduate computer science knowing a lot, you're going to need high-quality computer science. If you want people to pass the Advanced Placement in Computer Science exam, you need really high quality. It is very hard to get teachers to prepare their students adequately to pass the APCS exam. If your goal is to get more women and members of underrepresented groups into computer science, no, the quality isn't actually all that important. That's one of the surprising things that we've been finding in our studies in Georgia with Georgia Computes. And I just talked to somebody at Google. They've been doing a national study of similar sorts of things, what brings students into undergraduate computer science. And the reality is that having any kind of computer science at all in your high school dramatically increases the odds that particularly women and underrepresented minorities will go on to take some computer science. Here in Georgia, we found that white males will discover computer science on their own and will go into it whether or not they have it in high school. However, the correlation between women and members of underrepresented groups, so particular African Americans or Hispanics, who are in undergraduate computer science, they are far more likely than white males to have had some sort of high school experience. Now, that isn't causal yet, that's just correlational, but the folks at Google say that they actually have some causal data that they can show, here's two people, maybe two African Americans in two different high schools of similar quality, one gets access to computer science, the other one doesn't. This one is much more likely to go on to undergraduate computer science. So if your goal is to improve diversity in computer science, you've got to get computer science into the high school, period. It isn't that critical to have a great teacher. It is important to have a teacher.
And what about the goal of increasing computer science literacy among non-computer scientists? Do you think that's a valuable goal, and what skills should we be looking to teach non-computer scientists?
I think that is a huge and interesting question. Yes, that is a big focus for me. That's why I did media computation in the first place. Here at Georgia Tech, all undergraduates are required to take a course in computer science. And it's for the first 4 years, we had one course that met that requirement. And overall, the pass rate was around 78%, which is pretty good for a CS1, until you start splitting it out by different majors in different colleges. All of the majors from liberal arts, architecture, and management, all of those programs had around a 50% failure rate each semester, withdrawn failure rate. So students either withdrew or they gave up. So we really believe that everybody on campus needs to know something about computer science. But what we realized is that's not going to be the same course. It's not going to be the same computer science. So in media computation, we're explicitly teaching computing as a form of expression or understanding how the computer can be used for expression. So I really think that's an important thing for everybody to learn. I think, I don't have an empirical, a CS Ed research answer to your question, Dutch. I think it's a really great question. If you have computer science in high school, are you increasing the odds that your students will value computer science even if they don't go into computer science as a major? Will they learn things about computer science that they will use in the rest of their lives? I don't know the answers. I think they're really important. One of the things that I've talked about in my blog that I'd really like to see happen sometime is for an economist to estimate what is the cost in lost productivity due to computing illiteracy. all of the things that people do because they don't really understand what's going on in computing. You know, we know that most of the problems with cybersecurity is people problems. People who don't understand why you shouldn't name your password. People who don't understand why the things that their practices are dangerous in any way. There's similar issues. What is the cost of people not understanding that a byte is a byte is a byte, whether that byte is part of a JPEG, part of a Word file, or part of an instruction, and that's how viruses get into your system, because bytes can be anything. Issues of steganography, which is one of the things that I teach in my media computation class, the idea that it really doesn't take that many bits to define a text message or to define even audio. One of the things we do is hide audio inside of pictures. It's really not hard to do. Understandable text. So that's the kind of thing that I think that if you don't know these things, there are costs. It'd be great to estimate those costs to figure out how expensive is it that we don't know enough about computing in people's daily lives. And that's not even to count things about end-user programming. I mean, there's a bunch of evidence that says that for every software developer, there are between 4 and 7, some estimates go as high as 4 and 9, more end-user programmers, people who are not professional software developers but use programming as what they're doing. And that's today when we don't really support end-user programming pretty well. What if everybody had some computing in high school and undergraduate? How many more end-user programmers would we see in the world? And then maybe we really would see computing used as a form of literacy.
That is fascinating. I guess one question that comes to mind for me, I've read a lot of CS education. I've been involved in some CS education research. Sorry, read a lot of CS education research, and there's a lot of cool stuff that I've learned. But there is this theme that keeps coming back that's a little depressing for a CS education practitioner, which is, you know, what you do in your class really doesn't make a lot of difference in terms of the student's actual direct learning. Although you can make a difference in things like motivation and that sort of thing. And there are certainly things you can do to make a difference in learning. But I'm wondering if maybe what you said ties into that, and should we be continuing with that idea that if I can characterize going back to the quality versus just having CS education, if we can carry that on and say maybe what's really important in our university level education also is having the education there for as many people as possible, and maybe at least making it engaging education, whether or not it's high quality in a technical sense. I'm not sure quite what I'm asking, but maybe you know.
So I do think that our biggest lever that we can apply as computing educators is to improve motivation. Computing is hard. It is hard to learn Java. It is hard to learn C. It's even hard to learn Python. And if we can't change the languages, the main thing that we can do is to make it more interesting, more valuable, so as we make it more likely that students will be able to put in the effort to be able to learn. I think that the reason why it feels sometimes, like you say, Steve, that, well, what could we possibly do? Nothing that we could possibly do can actually make the learning easier. I think it's because we don't have enough tools in our toolbox that we feel that way. There are things that we know that improve learning. We can use things like peer instruction and pair programming and media computation. I think we have a set of things that we can do that improve learning. But I completely agree with you. The main thing that they're doing there is making it more fun to program. They're making it more worthwhile. You know, media computation, I produce interesting pictures and sounds. Oh, that's much more interesting than computing the nth Fibonacci number. So, okay, I'm willing to put in the effort to be able to create something interesting. With pair programming, we break down the perception that programming is a solitary activity, and so we create this social environment, and the students learn better. I think peer instruction is about changing the lecture. It's about getting students engaged. I think that does impact learning as well as increase motivation. But I think that overall, our main tool for teaching computer science is apprenticeship. Okay, I'm going to lecture at you for an hour. Maybe you'll get to watch me code, but then I expect you to go off and code by yourself for 3 to 5 hours in order to figure out what I told you in that 1 hour. And that's a pretty inefficient way of teaching coding. And teaching programming, teaching just about anything. Apprenticeship leads to really high quality results. People really do learn stuff if they're successful. However, it really makes for a very high bar to be successful. It's really hard, it takes a lot of hours. What could we do that is lower cognitive load, which is lower amounts of time, which does lead to CS learning? That's what we're exploring in this CS Learning for You project. We're creating electronic books to teach programming. And what we're explicitly exploring is this idea of, I'm going to bet that both of you, when you took math classes, or even when you took reading classes and English classes, occasionally you did worksheets. And given that the two of you are highly successful academics, you hated those worksheets. On the other hand, we have a lot of evidence that those worksheets were pretty successful for a lot of the students in just giving them activities which gave them practice. We don't have a lot of activities like that in computer science. Alan Kay talks about two-finger exercises, you know, that on the piano, learning the piano, there's certain things that you do over and over again just to get practice. That's like the worksheets. What does that look like as part of our CS Learning for You project? Let me give you one example. Steve, I'm going to bet that you have probably heard of Parsons problems. I don't know if Dutch has. So Parsons problems. It's named after Dale Parsons, who invented them, a teacher in New Zealand. I'm going to give you a programming problem. And I'm going to give you all of the lines of code which solve that programming problem on refrigerator magnets, and they're scrambled. Put them in the right order to be able to make the program work correctly. It turns out, some work by Beth Simon and Paul Denny, is that solving a Parsons problem requires about the same level of knowledge as being able to write the code in the first place. But when you're trying to solve a Parsons problem, you will never get a syntax error. Syntax completely goes away. But it's not like Scratch or Blockly, where it's a new language. It is the language that you're trying to learn. We can do Java, we can do Python. We've got both of those working with Parsons problems. Assemble the pieces. And we know that students have a hard time with this. There was a really interesting analysis of kids working on Parsons problems. Well, they'll move things in a certain way and press the check me button, and it'll say, no, there's a piece out of place. And they'll move it around and hit check me, no, it's still out of place. And then they move it back to the same position it was in a minute ago. And they hit check me again, right? They're not even aware that they're looping. So they actually come up with the same cognitive challenges that people do in programming. But to solve it overall takes way less time. I mean, we know that if you put it's while, parent, semicolon, before the left curly brace, that's a half an hour. It takes students about a half an hour to figure out that they made that mistake. That mistake will not ever happen with Parsons problems, right? So the idea is that Parsons problem is one of these class of activities that we could give to students to say, okay, you're not really getting it with the writing code. Try some of these kinds of exercises. For the highest ability, brightest students in the class, you might find these kind of boring. Though actually, Barbara Erickson is working on forms of the Parsons problems with distractors in them, some lines that you don't actually need. That increases the complexity of the problem significantly. And now it starts to be challenging even for the high-end students as well. But this is the kind of thing that's like those worksheets. I can reduce the cognitive load, I can reduce the amount of time, but it's still challenging and it still leads to learning. That's a class of activities that we need more of as CS educators. We have to have ways of asking students to program, of learning computer science, which isn't just, here's a problem, go hack that. I mean, we actually know from years and years ago, there was a lot of evidence that given a piece of code and a blank line, the code goes here, I mean, code, blank part, fill this in. That is a much easier task for students, but it still involves an awful lot of computing education, and students actually learn a lot from doing it. We need to do more of those sorts of things. We've got apprenticeship is a really great way of learning for high-quality learning. But we need things that help people to bring people along, to help people who aren't at the very top levels, ways of getting into computer science that aren't just go hack.
Okay, I think you just answered the question I was about to ask, but I'm going to ask it anyway, just in case you have more answers. And I was going to say, as I was listening to this, I've tried Parsons problems on exams, and I've been kind of disappointed with the results. And part of the issue is that I watch the students writing the Parsons problem, and they can't pick up this line and swap it with that line. They're just desperately trying to like, oh, this goes here and this goes here, and what did I have? And now I want to rearrange, and it's a whole nother 10 minutes in an exam to do that.
Yep.
And I was going to say, so how do I take that for my exam on Wednesday that I have coming up? It's drafted for my students out there who are watching.
I hope they're watching. Yeah.
But if I wanted to change it, if I wanted to get some of these ideas of reduced cognitive load but still a learning challenge, and I don't know about my students, but I think of exams as a fantastic learning situation. Mm-hmm. How should I do it?
That is one of the things the answer to that question is one of the things that Barbara is exploring in her dissertation. So Barbara Erickson is my collaborator and my wife, and is also a human-centered computing PhD student here at Georgia Tech. And she's been doing a lot with Parsons problems. She's been watching people do Parsons problems. We've been looking at log files of the books that we've built that have Parsons problems in them and see how people use them. And one of the interesting questions is, if you can't get syntax errors, what sort of errors should you get? What kind of feedback can I give you? How can I tell you you've been in this position before, you really don't want to try it again? Currently, all the Parsons problems systems that exist out there, the feedback you get is usually of the form, and these are mostly for Python, you have 3 pieces out of place, and 2 of them have the wrong indentation. If you ever play the game Mastermind, you have 2 colors wrong, and you have 1 in the wrong position, right? It's just, it's not enough, right? And so she's been exploring, how do I give better error messages? So, for example, one of the interesting ideas that she's exploring is, here's the garbled piece of code, here's the outline with indentation of what the correct solution is. Right? That's additional information. Now, we haven't tried this yet. This is just one of the things that we've been talking about doing. The other one that we've been thinking about doing is adding some semantic information to the blocks. Currently, all of the systems for Parsons problems know nothing about the code that's inside the blocks. What if you could tag them and say, this one has to be at the top of the loop. This one is initializing a variable. And what if you can now give, earlier Dutch was giving the example of putting in paren, as a way of teaching a particular practice. You could give as hints those sorts of things that you always tell students. This is an initialization of a variable. We always put initializations at the top of the code or the top of the loop, right? You could give people the kinds of things that you want them to learn as rules of practice, as rules of thumb, ways of doing programming. So I don't have an answer for you for Wednesday, Steve. I'm sorry. If you'd like to try the indentation one, giving the outline of the way the code should work, that might work for you, but this is a very active area of research for us right now that we're trying to answer this question. But I did want to catch on where you were saying the exam is a great learning opportunity. Yeah, there's all kinds of evidence. There's this really interesting testing effect. Taking a test improves your learning, period. So there's all kinds of evidence in psychology now where you take 2 groups of subjects. Both of them get a vocabulary quiz at the end. Both of them get to see the vocabulary words to learn from, but one group gets a vocabulary test first, before they've ever seen the words. They're going to get most of them wrong, but seeing the question primes the knowledge to think, what does that word mean anyway? And then they end up, when they see the words, they learn them better, and they do better than the other group when it comes to the final test. And there's this great work by Michael Lee and Andy Coe with their game Gidget, where they're teaching computer science, where they inserted into Gidget a multiple choice question. When you solved that problem, how many times did Gidget have to go through that loop? So many, and you have the various choices. One of the surprising results is adding those sort of multiple choice questions got people to play the game longer. Now, why did it get them to play the game longer? Was it more engaging? Did it lead to more reflection? Did they learn more because of the question, which then made them more successful in the later levels? I don't know. It's an open question as to why that had the effect that it did. But adding these exactly like an exam question, a multiple choice question, adding that into the game Gidget actually improved gameplay. It made people stick around longer.
That is totally fascinating. It's excellent. I think I was going to mention we've got about like 15 minutes left, and I've got about 45, 50 minutes of questions at least. Dutch, you probably got another.
Yeah. Oh,
the
sure.
same. So let me hand off to you, Dutch. I think I've taken more questions than you. Do you wanna take
okay.
one?
Well, so this is just a person. This is more of a personal interest to me. You've mentioned media computation a few times.
Mm-hmm.
I'm sure you're familiar with HyperCard.
Yeah, I loved HyperCard. Actually,
I started on HyperCard in high school. Actually, before high school. That's kind of the first programming language for me. So, I want to ask a question about that. I guess my question is, what happened there? Why don't more people use this?
That's a fascinating question that I don't really know the answer for. But I've asked people like Alan Kay, why did HyperCard go away? And by the way, it's not completely gone away. Have you played with LiveCode?
No, I haven't played with it since. I essentially started HyperCard. All my friends were playing with it. We had a great time. Eventually, we hit the wall where we wanted color. We couldn't get color without putting in X commands in C, and that jumped me to C, and I was a C programmer from then on.
Yeah, I did my dissertation in HyperCard. I built a system for students to learn physics and programming by building physics simulations, and it was all in HyperCard. I actually spent more than a year of my life programming in SuperCard, but the bugs of SuperCard were really big and deep, way worse than HyperCard, and I just never could get past issues of garbage collection, and you can't get the source. It's very frustrating. But anyway, live code is really neat. I think it's really exciting the number of platforms you can build for that with the same live code stack. You can generate an Android app or an iOS app. They've just done a Kickstarter funding that they're going to build HTML5 as an output engine. So be able to build in HyperCard and generate an HTML5 application, which I think is really exciting. I think that what it really Steve asked me a question about what as instructors, what can we do to help our students learn? And the main thing that we can do is motivation. That we can make it more valuable. There are things we can do like peer instruction, which really does improve learning, but for the most part, things like media computation are about changing the value of programming to get kids to do more. I think that what happened to HyperCard is an answer to the question, what demotivates people? What keeps people from going deeper into computer science? And I think that one of the things which happened to HyperCard is that it got dissed by the computer science establishment. Talk to most programmers, professional programmers who knew about HyperCard, and they'll tell you, oh, it was so wordy. Oh, it's just so ugly. I mean, I can't format the code that way that I want. I've got to use these thes. Why would I have to type the anywhere? But that was actually a critical part of the syntax of HyperCard. So it's this really interesting situation where I think that a lot of the value for HyperCard disappeared because when people were learning programming and talked to professionals about programming, they were disrespected for learning HyperCard. Now, there's a similar kind of thing going on with Scratch. Now, for the most part, people say, well, Scratch is this kid's language. It's okay. It's an educational language. But you still get the sense, a very strong sense, but we want to move kids away from Scratch one day, right? They've got to move beyond Scratch. And it's that attitude which says to the students, oh, Scratch isn't real. Scratch is a toy. And I don't really have a good solution for this because Scratch is a great tool. Scratch is a great way of getting started. But I think that people do get a message that it's better to go learn something real, and real in quotes, because what somebody perceives as real depends on who they're talking to.
Do you think it might help to incorporate a more widely used language like Python so that you can be working in Scratch and then call out to some Python in the same way, though perhaps a lot easier than the kind of Xcommand stuff from the old HyperCard days?
I think that would be really cool. The question is that would it make people feel comfortable with the tools that they're using? I was at a workshop in March where at Stanford we were talking about the future of computing education research, and somebody was talking about work that they were doing with computational scientists, and the computational scientists, for the most part, still work in things like Fortran. I got a chance to give a talk at a NASA research center at Goddard a couple years ago, which was fabulous fun. And the most common programming language there is Fortran. And at this workshop in March at Stanford, people started saying, that's terrible that they still work in Fortran. We've got to go fix them. We've got to go get them to use real programming languages with real supports for for more complex code. And I started doing the thought experiment. Imagine you grab a group of researchers in this community and say, you're not going to use Fortran anymore, you're going to use Python, NumPython, whatever you want. It could be F#, it doesn't really matter. But we're now going to cut you off from your community. You won't be able to use code that other people in your community are building. You won't be able to talk to other people about your code because you're going to be using some weird language, right? It doesn't work. In education research, we talk about communities of practice. Jean Lave and Etienne Wenger wrote this book called Situated Learning. And people say, oh, it's about apprenticeship learning. It's not. It's about all learning. All learning is about becoming a member of a community of practice. Dutch, you want to be a computer science academic. It's not to say you are already, but when you started on this path, you wanted to be a computer science academic. You engaged in activities, maybe as an undergrad, that you got involved in undergraduate research. If you're involved in undergraduate research, it doesn't mean that you're writing a Chi paper. It means that you're helping out with things. You may be running subjects. You might be doing some data analysis, writing some code. That's called legitimate peripheral participation. You're actually doing something which is useful, but you're not in the center of the community of practice. But while you're doing that, you see people in the center of the community of practice and say, I want to be like them one day, right? And so eventually you go through stages where you become part of the center of the community of practice. That's what the goal of all learning is from a situated perspective. Okay, what happened to HyperCard? So where was the HyperCard community of practice? And who was at the middle of it? And did you really want to be that one day? That's the problem. Right? So it's actually really easy to teach kids Perl or Ruby if the community of practice that they want to join in, what they value in terms of what they want to be when they grow up, if those communities use Perl and Ruby. Right? So in the end, it's not about the factors of, it's not about the language itself and its features. I mean, those things matter. I just had long discussions on Sunday with my daughter and her friends about what public static void main string bracket bracket args mean. That is really complicated for them to wrap their heads around. The language features do matter, but the more critical thing is, what do you want to be when you grow up? Who do you want to be like? What do they value? And kids who are learning HyperCard were being told, I mean, particularly if they got really into computer science. I mean, clearly that's how you started, Dutch. You got into HyperCard. You wanted to be a programmer, and if you ever talk to any professional programmer about HyperCard, oh, that's a nice toy. Yeah, when you grow up, you can come learn toys, you learn languages like mine, right? And HyperCard then dies eventually. And I don't know how to fix this. It's sort of a cultural issue. We have to be able to say, oh, HyperCard is cool. I'm glad that you're doing HyperCard. Show me what you're doing. And for there to be reasonable paths out of HyperCard, but we need to, for HyperCard to continue, there had to be a group of professionals which use HyperCard all the time that people could say, oh yeah, that's cool. I'd like that to be something that I can do one day. I mean, maybe what we need to do somehow is to make end-user programming communities not so invisible. We need kids in high school to be able to see, oh, you know, besides professional software developers, besides professional computer scientists, there are a lot of people who program. And there are people that do things like you want to do. I mean, like, everybody's studying science and engineering, they should see computational scientists and engineers. They should see this is what you're going to be doing one day. This is going to be part of your practice, so you should value it in that sense. I mean, you don't have to become a professional software developer, but you should value code as a way it's going to help you answer questions and express yourself and communicate with others later. Does that help?
Absolutely. I'm reminded of, so I work with the startup company. We build a big storage appliance. We work in a wide range of programming languages. We have front ends in Python. We have JavaScript UI. It all comes back to C programming at the core. It seems like part of your answer is you need that kind of range of interoperability to see how any part there can be useful and can work with other communities.
I'm saying something slightly different. Mostly, I think you're right.
I want to get away from the idea that you have to move towards C, right? But
the value of the interoperability isn't that, oh, it's okay for me to work in Python. The value of the interoperability is for you to be able to say, all of these different languages have value. And if you're programming in Python, that has value too. So
right.
interoperability has a cultural value to you, and that cultural value within the organization means it's okay to work in Python. You are still doing something which is legitimate for our software development.
Exactly, that's what I'm trying to get at, yeah.
Mr. Interviewee type person.
That's me. I'm the interviewee type person. All right, so we've come to the end of our time, which is incredibly sad because I want to talk more. So first of all, I want to say thank you very much to you, Mark, for being here with us. This has been a fabulous episode. I'm going to be rewatching this a few times, maybe before my exam on Wednesday, and maybe before my class tomorrow at 9 a.m. That's my live coding class tomorrow at 9 a.m.
Oh, cool. Very cool.
So
thank you very much. Dutch, thank you so much for guest hosting. That was fabulous.
It was fun. Thanks.
All right. And we always give our guests a chance to do any shout-outs that they'd like to do. You mentioned a lot of researchers and work and educators you're interested in. Is there anybody else you want to mention?
Yeah. More people should go read work by Betsy DeSalvo. Betsy does some of the most amazing work in understanding why kids might want to not learn computing, and about phrasing computing in ways that appeal to their values, not just their interests. I think that she's really great, and more people should know about her work. But yes, shout-outs to Barbara Erickson and Brianna Morrison and Miranda Parker and all of the folks here and all the folks in the BPC community. I wouldn't be doing what I'm doing if it wasn't for people like Jan Cooney and Jeff Forbes. Thanks to all of them. And thank you both for having me. This was a lot of fun.
You are most welcome. All right, and I'm just going to mention for the record, BPC is broadening participation in computing, and with that, I think that is our CS Education Zoo episode number 6. Thank you all for watching, and we'll see you next time, possibly the Hacker School episode. We're trying to figure out exactly what will come next, but we'll keep you posted on Twitter and on our website. Bye-bye, everyone.
Bye.